So the last two classes that we've hung out together, we talked about root locus. So the first time we talked about the angle criterion, which told us whether or not a pole was on the root locus for any value of k. We talked about the magnitude criterion, which helped us solve for the value of k for which a pole is on the root locus. And then last class we talked about drawing the root locus. So we talked about the set of rules that we follow that help us figure out where the poles, the open loop poles and zeros go, where the branches go, and how those branches behave as k goes to infinity. And today we are going to talk about how to use the root locus as a design tool for figuring out what our controller should be, what our controller should look like so that we have a particular behavior of our system that is desirable. Okay, I probably should have said this first, but just some announcements. You of course know that you have homework 4 due Thursday. You will also have quiz 3 in class on Thursday. And that quiz will be focused on our steady state error and our root locus. Yes, John?
Will exam 2 be between quiz 4 and 5?
You can assume that exam 2 covers everything after exam 1.
I think exam 2 is, right now, according to your schedule, it's supposed to be November 6th, that Thursday. So.
Yes, whatever's on the syllabus is true for when it is. I'm just talking about what's going to be covered on it.
Okay.
Yep.
Thank you.
Okay? Oh, sorry, you were talking about timing.
Well, I just wanted to, I was asking in a roundabout way what was on it and also when it was, but both questions were answered.
Okay, great. As long as both are answered, we're good. Thank you. Alrighty. So, for today's discussion, let's recall our unity feedback system. So we'll draw what that looks like. We've drawn this system over and over and over and over again, so hopefully you're getting familiar with a unity feedback system. We're going to talk about a controller or a compensator and a plant. Not this type of plant. Right, but a dynamical system that describes the physics of what we're trying to control. And why am I not drawing a block on the feedback loop?
It's unity.
It's unity feedback, yes. So we are, in essence, assuming there is a block here, but the value within that block is a 1. So it's unity feedback. This is a plus, this is a minus, this is my output C of S. Okay, and within that compensator, we're going to talk today about a K gain and an H of S, which is a transfer function that we get to choose. We get to decide what H of S is so that we get some overall closed loop behavior that is satisfying to us. And of course, as always, we call our plant transfer function G of S. Okay, so today we actually get to put on our control engineering hats. Today we will choose the compensator that achieves the closed loop behavior that we want. Okay. And today we're going to talk about a very special system, just as a motivating example. I know this looks like a double-headed fly swatter, but squint your eyes and pretend it's a satellite for me. So we've got a satellite out in space. Turns out, seems like a satellite out in space would be a really, really complicated plant, but when we're out in space, we don't have all that much gravity going on. So gravity's not really there. We don't really have all that much wind resistance. There's very, very little air, so it doesn't resist a whole lot. So we really just have this thing floating out in space that potentially has a method for applying torque to itself. Who knows what kind of mechanism is usually used to apply a torque to a satellite? Thrusters is one way. Yep. Or I heard it. A flywheel. Yeah. So flywheel is like this idea that if you spin in one direction, you'll get a reaction force spinning the other direction, or a reaction torque. Okay. So that's all we're going to assume that we have. We'll say, regardless of what kind of mechanism is causing it, we'll say we have some torque that we can apply to this satellite. About this, we'll just consider one axis of rotation along the length of the satellite. And maybe this satellite has some inertia, this mass moment of inertia I. So mass moment of inertia is like the rotational equivalent of mass. So mass is a resistance of a body to accelerate linearly, and the mass moment of inertia is the resistance of a body to accelerate angularly. So it's resistance to angular acceleration. Okay, and then what we're wanting to control is some output theta or theta dot. Okay, so this is the drawing of our plant. All right. If we were to do our first principles analysis to get our equation of motion, we would say that the torque on this thing is equal to I theta double dot. And what did I say was our output? Let's go ahead and analyze output and input. Output is theta, yep. Here, I'll just do this. And input is what? Yep, is anyone else other than Alex awake?
Torque.
Torque, thank you, Angela. Angela's awake. Torque. We as the engineer, we get to apply that torque. Okay, so if I wanted my transfer function of this equation of motion, what should I do? Am I in the right domain? I have functions that are a function of time. Are transfer functions in the time domain? They're in the frequency domain, which requires that I use a Laplace transform. Yes, so I need to Laplace transform both sides. Ooh, buddy. Sounds like everybody is having just as hard a time waking up as I am. Okay, Laplace transform both sides. I'll end up with some capital T tau of S equals I is just a parameter, just a scalar number. S squared capital theta of S. The output is theta, so if I want output over input, I want theta over tau. So if I divide each side by tau and I divide each side by I S squared, I should get output over input equals 1 over I S squared. So this is my plant transfer function. Okay, let's look at what that looks like in our block diagram. Let's start out by just assuming we're going to choose some very simple K gain. This is why I don't write on whiteboards, because apparently I suck at estimating space. This is my compensator. I plop in my transfer function for the plant. Plop. All right. Let's draw a root locus. Let's draw a root locus and see if we can figure out the ways in which this thing will behave. Question? Here? Yep, good. Thank you for asking. Okay. What is the first thing that I put on a root locus? What type of poles, Angela?
Loop poles.
Open loop poles and open loop zeros. Do I have any open loop zeros? Nope, I just have, if I were to reduce this down to a single block diagram, I'd have K over IS squared. That K is not a zero, it's just a gain K. But I do have two poles. What types of poles are they? What makes the denominator zero?
It's just a repeating pole at 0.
Yeah, it's just a repeated real root at 0. So s equals 0 causes this to be 0, and then s equals 0 again causes that to be 0. Okay, so I will put my real repeated root. I like to use different colors to show that they're both there. Okay? Okay, tell me about branches on the real axis. When I'm drawing my root locus, the rule is that I put a branch on the real axis when I am to the left of an odd number of poles or zeros. Okay? So, should I put a branch out here? No. Should I put a branch here? How many poles am I to the left of?
1, 2.
Whoa. I heard 0, 1, and 2. I'm thinking that this is a pole that's black, and I'm thinking this is a pole that's red. So I'm to the left of 2 poles. Okay? So I'm to the left of an even number of poles. I don't put a branch. Okay? So where the heck are these branches going? They can't go to the left or the right. They go straight up and down. They go straight up and down. Do they, actually, tell me, do they go off at any certain angle? They go off at 90 degrees because there are 2 poles that are exiting the real axis at a single breakaway point. So the rule there is that at every breakaway point, the angle to the branch, number of branches that are leaving is 180 over the number of branches that are leaving. So there's 2 branches leaving, so I have 180 over 2. So each one is leaving at 90 degrees to the real axis. All right, if this is sounding foreign to you, I'd highly suggest going back to your notes from the root locus day, okay? Okay, so what does this tell me about the behavior of this system? Okay, it's purely oscillatory. Why?
Because it's entirely on the imaginary axis.
Yeah, is that true for any particular k value or?
Yeah, it's true for any k value.
For any k value. Okay, so what this means is that if I give this thing some input, let's say I want you to go to 90 degrees. It is not ever going to settle at 90 degrees. Because I have purely imaginary poles, it will always oscillate. It will continue to oscillate forever because there is no damping. I'm purely oscillatory. And this is true no matter what the k value is. So my open loop poles are essentially a k value of what? Open loop poles are a k value of 0, okay? As k gets bigger, my poles are going to pop out onto the imaginary axis, but they will never exit the imaginary axis. That's what this root locus tells us, is that as k gets bigger and bigger and bigger and bigger, all that's going to happen is those oscillations get bigger and bigger and bigger. But they never damp out. Do you think that's the behavior we want for our satellite? No, so you're an astronaut in this satellite. I don't think you want to be bashed around like that for the rest of your life because the control engineer didn't look at his root locus. Okay? So, let's take a quick note on that. All right, so the behavior here says that no matter what we do with K, this system will never settle at our desired angle. Well, crap. So what do we do? What do we do as a control engineer?
Change the compensator.
To what?
PIP.
No matter what K is, I'm screwed.
Don't you add feedback control on it?
Let's pretend we only want to deal with this block compensator where I've put it.
Can't you add another pole?
Ah, yes. We, in fact, as engineers, are not limited to a proportional gain K. We can do fancier things than that. We can instead add a pole, or even a zero, or multiple poles, or multiple zeros to this compensator block. We get to choose that. We get to choose whatever goes in that block to make this thing behave the way that we want to. So we're not restricted to K. What if, in fact, I said, let's look at what would happen if we were to add a pole to this system, and let's look at it on the root locus. Let's pretend I don't have all of these extra gain values marked out. What happens if I maybe added a pole at maybe some minus A? Where would my branches go then? Am I still stuck with this thing where I go up and down to infinity? No. Okay, so I still will not have a real branch here. I need to be to the left of at least one polar zero before I start adding real branches. Do I add a branch here? 2 poles right on top of each other.
No.
Am I to the left of an odd number of poles? No. Alex takes it back. Okay, what about here? I'm now to the left of 3 poles or zeros. 2 poles at 0, 1 0 at minus A. So yes, I do now have a real branch going this way. And so if I start out at poles, my branches start at poles and they end at zeros, I've got to somehow come out of those poles and somehow return to the 0. So I'll have 1 infinite 0 and 1 finite 0. Okay? On this, with this root locus, is it possible for me to choose a value of K such that my system will approach my desired angle? I see some nodding. Yes, why do you think that?
Because there's a pole that's entirely on the real axis.
There is a pole that's entirely on the real axis. So remember, if you have any amount of pole on the imaginary axis, you will have some oscillation. Now, that doesn't necessarily mean that these poles will oscillate forever. In fact, they're underdamped poles, right? So that means that it'll go oscillate, and then it'll damp out, and it'll approach our final value. So yes, even basically all of these poles will eventually approach the desired value. But what if we wanted absolutely 0 oscillation? We said, okay, my astronauts get motion sick really quickly. Let's not jostle them around at all. They're just really sensitive astronauts. Is there a K that I could choose that makes it so there's 0 oscillation? Alex says yes, because it is possible for me to choose poles that are entirely on the real axis. So in fact, these are going to be overdamped poles, but there is a spot right here where I have critically damped poles, which will very nicely raise up quickly enough to our steady state value that we desire. Okay, so well done. Good job, control engineers. You chose a new form of our compensator. So instead of K, so let's say what would happen if I add a 0 to my compensator, well, at that point, the world is our oyster, and we have all sorts of options that create behaviors that are more desirable than we had without that 0. Okay, that said, today we're going to cover in depth this idea of PID control, which is like your peanut butter jelly of control engineering. If you walk out of this, this is like the third thing that I want you to remember 5 years from now. The first thing was, I think, right half plane poles bad because it means instability. The other one was the general form of a state space equation, x dot equals ax plus bu, y equals cx plus du. This is the third one. The third one is PID control, okay? Let's talk about what PID control means. So to explore this, let's go back to our unity feedback system and play around with the math there a little bit. Let's go back to h of s equals to 1. That's where we had our compensator was just that proportional k. So we're assuming that the compensator always takes the form shown here, k h of s. So if we want to look at just that proportional feedback term, h of s must be 1. So let's look at that case more closely. So if h of s equals to 1, let's actually add in a couple of signal values here. What do you know about the signal on this arrow here? It's the error signal, absolutely. Yeah, so let's give it a letter. We'll call it E of S, error. And then what do we usually say comes out of the controller? The actuating signal or our control signal. We'll call that U for today. Okay? I say this because I want to refer to what's in our compensator box as U of S over E of S. Okay? So we have our output over our input is what comes into or what's in our compensator box. Okay, so let's go back to H of S equals to 1. If I have U of S over E of S equals K H of S, and H of S is equal to 1, I just have K. Let's go back. Let's reverse Laplace transform this, inverse Laplace transform, try to figure out what our control signal is in the time domain. So I want to know what is our control signal U in the time domain. So I need to multiply by E of S. So I'll have U of S equals K E of S. And if I inverse Laplace both sides, inverse here, oops, I should get U of t, the control signal in the time domain, is equal to still just some proportional k times our error. This, my friend, is usually labeled with a subscript p, and it is referred to as a proportional gain, kp, because what you have just created is a proportional controller. Why do I say it's proportional?
Because the error is multiplied times the proportional term.
Yes, so our control input is just some number times our error signal. So our controller is always proportional to the error. We will refer to this as our P controller. Okay, so let's think back. When I developed this P controller, I put a K value in my compensator box. Did I add any poles or zeros to the system? No, I just multiplied by a K value. So a P controller adds neither poles nor zeros to the system. All right, let's kick it up a notch. Let's look at what happened when we added that 0 to our system. So I'm going to cordon these off because these are different things we're going to try for h of s. So now let's try h of s, bless you, equals k s plus a. Let's do it again. Let's see what our control signal is in the time domain for this choice of compensator. So I have u of s over e of s equals k s plus a. Let's solve for u of s. And I'm going to break this up into two different terms here. So we'll do k s e of s plus k a e of s. And we'll inverse Laplace both sides. Just get u of t. What does this multiplication by the s term do? Remember, of course, that you can always go back and look at your Laplace transform tables, but this is one of those ones that you probably should have memorized.
It's like a derivative.
It's the derivative, yes. When I multiply by an s in the frequency domain, it's the same as taking a derivative in the time domain. So here I have k times e dot of t. All right, there's no s on this second term. K and a are just both scalar values, so this is k a e of t. Okay, everything that multiplies that e dot, we refer to as our kd. What do you think the d stands for? Derivative. Very good. We still get something that multiplies by our a, so we still have a kp. We still have our proportional term. So this is what we call proportional derivative control. Or PD control. Yes.
Yes.
Sorry.
So you're good. So is it typically not like normal, or I guess like not usual for you to only use the derivative term, because like would that just mean that a would be equal to 0 then? Because you wouldn't get that extra like component.
Mm-hmm.
So, but like in reality, you would never just use the derivative portion, right? You would always like have it combined as like a PD.
I can't think of an example where you would only use derivative control, but it's basically like if you only did derivative control, you would just be adding damping to your system.
Okay.
So you'd always have steady state error? If you only have damping?
It depends on your system and the input to the system. Remember, our steady state error is a function of our input. But the derivative control is not what will take care of our steady state error. The one we're going to talk about next is. Yes. Very good questions. Okay, using your pattern recognition skills, what do you think is our next controller? What do you think it's called? The integral controller. Yes, we will call it I control, or better yet, we'll continue to add a proportional term and we'll have PI, or proportional integral control. Okay, so let's try, actually, I wanted to add one more note here on PD. On PD, let's note that PD controllers add 1, 0, but no poles to the root locus or to the system. Okay. Now, let's try H of S equal to S plus A over S. So I'm adding a 0 at minus A, and I'm adding a pole at S equals to 0. All right, so this says that U of S over E of S equals K times S plus A over S.
You got rid of the proportional?
I still have my K.
Did you
Oh,
have
I
the-
see,
oh,
okay.
never mind.
Remember, in that compensator box, we have K H of S.
Is
Okay.
it supposed to be part of H of S the way you defined it then?
In the last one, you put K.
Yeah, okay.
So take it out of the last one.
Yeah, it technically shouldn't be in the last one.
Okay.
Sorry. Yes, okay. Now we're consistent throughout. But U of S over E of S is the combination of those two cascade blocks. So it does have the K in it. Yes. Thanks for keeping me honest. Okay, let's do it again. So U of S equals K E of S times S plus A over S. And let's break that into terms here. So this will be, let's see, K S over S plus K A over S, all times E of S. And then I can distribute the E of S. So I'll have K, my S's cancel, times E of S. On the second one, my S doesn't cancel though. I'll have K A over S times E of S equals U of S. And now I can inverse Laplace transform both sides. Minus 1. All right, if multiplying an S gave me a derivative term, dividing by an S gives me an integral term. Very good. U of T equals just K E of T plus K A times the integral of E of T dt. What do you think we call this first K? KP, because it is just a proportional term times my error signal. And what do you think we call this KA? K sub I. That's my integral gain. We call these Ks for PID control, we call them gains. I have a KP, a KI, and a KD gain. PID gains. Okay, so we call this proportional integral control, or PI. So what did we add to our system this time? Remind me. How many poles did we add? Specifically at S equals 0. And how many zeros did we add? also 1, and specifically at a real value, s equals minus a, yes. So PI controllers add a pole at the origin and a 0 elsewhere, but on the real axis. What do you think our last example is going to be? PID, full PID. All right, lastly, we'll try one last form of h of s. We'll say h of s is s squared plus a1s plus a0 all over s. Which makes our u of s over e of s equals to k times this. I'm going to split it up into terms already. So I'll have a k times s squared over s plus a k times a1s over s plus a k times a0 over s. Okay, there's going to be some canceling that happens here. We'll go ahead and cancel and multiply by e of s. So we'll have a ks e of s plus a ka1 e of s plus a ka0 over s e of s. You should go ahead and already be able to tell which term is the proportional, which term is the derivative, and which term is the integral. Right? So what is this one here? Derivative, because I'm multiplying by an s. What's this one? Proportional, there's no s's. And what's this last one? That's my integral, because I've divided by an s. Very good. Okay, inverse Laplace. Sorry, I'm going to be lazy here. I don't want to rewrite it. Bless you. U of t equals k e dot of t plus ka1 e of t plus ka0 integral of e of t dt. Here we have our kp. Nope, sorry, kd. kd, kp, and our ki. Proportional, integral, derivative, control. What did this controller add to our system in terms of poles and zeros? How many zeros?
1, 2.
So we added an s squared polynomial in the numerator. If we factor that, there's going to be two s's, two s terms that could cause that to be 0. So I'm adding 2 zeros and 1 pole at the origin. Okay? So PID control adds a pole at the origin and 2 zeros elsewhere on the real axis.
specifically at H of S when you determine that?
Yes.
Okay.
My guess is you're asking
I
because
was
of K.
looking- Yeah, I was looking after we already distributed it out, and I was like, that's why I was confused, but, okay.
Does the K value add any poles or zeros, though? No. So I can look at just the H.
Okay.
Yep. All right. Let's do an example of some design work. So let's go back to our satellite. Example here. Let's try to get our satellite. Does satellite have 2 T's or 3?
You're asking the wrong group of people.
There's
We're-
one T in the front,
And 2 L, yeah, so 2 T's, so like
one in the front,
one T in the back.
Okay, so just 2.
yeah.
That doesn't look right to me, though.
There's 2 L's,
Two
there's 2
Ls.
L's.
There you go.
That still doesn't look right.
According to Google, it's correct.
Okay, I just need another cup of coffee, apparently.
At least it's not the ant.
Okay, to behave with a settling time of TS equals to 1 second and a percent overshoot of roughly 0%. So let's remind ourselves of what happens if we just use proportional control. So remember, this is the very first root locus that I drew this morning. Our system had 2 poles at the origin, and the branches go up and down to infinity. Is it possible to get a settling time of 1 second if I only do proportional control? No. It won't settle. It will never settle, right? So we have to add something other than a K value. Okay? So we said, in fact, you already told me that if I just add a 0 to this, I should be able to get some desired behavior. Okay? I can basically choose my settling time at that point, and I can choose my overshoot. Now tell me about this percent overshoot equal to 0. What does that tell me about like the poles that I'm looking for? Josh?
Does that mean that the system is critically damped?
It means the system is critically damped. Absolutely. Yes, so critically damped poles are what type of poles?
2 repeated.
2 real repeated roots. So I'm looking for 2 roots that are exactly the same on the real axis. Yeah.
Couldn't it technically also be overdamped? Overshoot is zero?
Yes, I think yes. But do you remember what behavior we talked about? What is the difference in behavior between a critically damped system and an overdamped system? Do you remember what that behavior difference was? It takes longer to settle. Yeah. So one of these specifications is going to set one of those things in place and make it so that the other one can only be critically damped. Yep. Okay, so let's see. I'm going to erase my only proportional root locus here. So what do we need to figure out? We essentially we know that adding a 0 is going to give us the behavior options that we want, but we need to figure out what about that 0.
Which one? Zero?
Where should I put it? Yeah, so I don't know. I know that if I add that 0, my branches will look... Sorry, this makes it look like I have an open loop pole. I was trying to draw a closed loop pole. My branches are going to come out here somewhere, symmetrically, I can't draw symmetric because I'm human, but pretend these are symmetric. They're going to come together at a single break-in point. One is going to go in towards the 0. The other one is going to go out towards infinity. And we need to know, actually tell me, what sets the, if you were to draw a settling point on this graph, how would you draw a settling point? I'm sure you all have this memorized, that settling point is 4 over zeta omega n. And we also know that zeta omega n here is the real portion of your poles, right? So I can draw a line on this graph that gives me the settling time that I want. Okay, if I want settling time to equal 1 second, then zeta omega n better be what? 4. So that means that my real component of my poles sure as heck better be -4. Okay, so I want to place my poles anywhere on this line here. Okay, and then we also need to figure out, let's see, where should we put the 0 such that the break-in point, where it is critically damped, is at the same spot where my settling time is the value that I want. So I need to figure out, where does this 0 need to go such that the break-in point is at -4. How do you think I might choose that? We actually can go back to our magnitude criterion. Let's write out a note here. So where should we put the 0 such that the break-in point is at -4? If we go back to last week's notes, the break-in point, we found the break-in point by saying, okay, let's find the K value that causes K of sigma, which is K with only real values plugged in, to be at an extrema. So we took the derivative and we set it equal to 0, and we solved for that K value. That's how we found out where our break-in point is. So now we can plug in the form of h of s that we would like. We can set our break-in value at the position where we want it and solve for the a value that causes that to be true. Okay, so that's just a little foreshadowing. Let's plug and chug and see what we can figure out. Okay, so we need to take the derivative and set it equal to 0. So if we're going to add a pole to our system, let's remind ourselves g of s here for our system was 1 over is squared. And we said we want h of s to be of the form s plus a. We wanted to add a 0. So g of s, h of s is what?
S plus A over I squared.
Beautiful. Okay. So K of sigma should be minus the inverse of G of S, H of S. So minus I s squared over s plus a. This is k of sigma. And I want to take the derivative of this and set it equal to 0. So d sigma, oh, sorry. I did not plug in my sigmas here. Equals, ooh, there's sigmas in the numerator and the denominator. Dang it, Alan says. What do we have to do to take a derivative of that?
Quotient rule.
Quotient rule. Low d high minus high d low over low low. Okay, so what is low? Sigma plus a. Low d high, so minus I 2 sigma. Minus high d low, should just be 1, all over low low. And we need to set that equal to 0. Okay, so we know from last week that our break in and break out points will appear when this expression is true. So let us simplify this a bit. We will say, let's only worry about the numerator being equal to 0. So if I multiply by sigma plus a squared equals 0, I just get 0 equals the numerator. And then I'm going to distribute some stuff. So minus I 2 sigma squared minus I 2 a sigma plus I sigma squared equals 0. All right, I have 2 sigma squared terms. Let's try to combine those. Should have minus I sigma squared minus I 2a sigma. Let's factor out a minus I and then divide by it. And it looks to me like I can factor out a sigma. Okay, so our break-in point, well, actually, tell me, in our root locus, if we go back up, do we have both a break-in and a breakout point? Yeah? Which do you think is our breakout point? Sigma equals 0, right? We already knew that because we had both of our poles at 0. We know that's our breakout point, which means our break-in point has to be when the other term goes to 0. So this is the location of the breakout point. This is the location of the break-in point. And that's the one that we wanted to control, right? We want to set where that break-in point happens. So I want this thing to be 0 when sigma equals what value? Minus 4. I want this term to be 0 when sigma equals minus 4 to cause the break-in point to occur here. Okay, that's easy enough. We'll say when sigma equals minus 4 plus 2a, I want this to be 0. I can solve for the a that does that. What value of a gets us there? 2. Brilliant. Okay. Are we done? No. What else do we have to decide?
We have to plug that in to get a settling time.
So this tells us that there is a value of k for which I can achieve the settling time that I want. This 0 allows that to happen. Do I know what value of k? If I look back here and I say basically what we've decided as an engineering team here is that this is -4, this is 2. Okay? I know that I want to choose the poles to be right there, but I don't know what k does that for me. I don't know what k value. Remember, the open loop poles and zeros are here for k equals 0. I know I have to increase my k past 0, and my poles will start to come out here, out here, out here, out here. We're getting close. We're getting close. At some point, they will break in, but I don't know what k value that is just yet. I need to solve for it. Okay, let's go back to our magnitude criterion one more time. Our magnitude criterion says that k is equal to -1 over g of s, h of s. I now know exactly what h of s is. I know that h of s is sigma plus 2. So this is minus I sigma squared over sigma plus a. This really should be s. I apologize. Plus 2. So this was the a value from above. Yep, Jerry?
Could you explain where we got the -4 plus 2a? I know -4 is the root you want, and the 2a is from, I see, okay, location of breaking point.
Yep. We're trying to force that break-in point to happen at that particular value of s, which is a real value of -4.
Thank you.
Yep. Okay, and again, I'm wanting to know what is my k value when I'm exactly at that s value of -4. So let's plug in -4 and figure out what is our k value. So here we'll assume some value of our mass moment of inertia. Let's just say 10 for today. We'll say -10 times -4 squared over -4 plus 2. This should give me 160 minus 160 over -2. Gives me k equals 80. Okay, so we decided that the final form of our compensator should be 80 times s plus 2.
This would be a proportional derivative controller?
Yes. Yes.
So
Angela.
did we already figure out the deal with, the percent overshoot by just saying that like for it to be 0, like the zeta value has to be very close to 1 or at 1? Like, is that how we already just like figured out
Yep.
that one?
Yep.
Okay.
We decided that we needed to be critically damped.
Okay.
Yep. Okay, let us use our engineering tools aka our friend MATLAB. Let's do the same thing with MATLAB. Oh, come on.
No, I get that, because it's like, it says you can have one and this will change. I mean, close to one, because if it's one, it's a zero, that's fine.
Okay, we might not be doing it on MATLAB because my computer just died. What? How does this desktop not have MATLAB on it? Okay, that's wild. All right, you know what? I will post the code that shows this example in MATLAB. You can trust me. It does in fact work. So what we would do is we would put this system, we would create our transfer functions for G, H, we can multiply them, create the closed loop transfer function, we can plot the root locus of our G times H. Angela, question?
You can finish first, I just have a question from the last, problem we did.
Okay. If you plug in your GH into your root locus with the chosen values, you should be able to hover over the branch and you will be able to see that the K value is 80 at the point where we break in at -4. And you can absolutely confirm that the break-in point happens where we want it, and it happens for a K value of 80. Okay? All right, I'll post that code. Otherwise, that's all I have for you today. Questions?
Yeah,
Angela?
I'm still confused about the percent overshoot, because if you assume that, the system's critically damped, zeta's equal to 1, right?
Zeta equal to,
Yeah,
yes.
so when you plug in zeta equals to 1, you have like an exponent of pi over 0, which is undefined, but I'm like confused on how that makes zeta, or, I'm sorry, how that makes the percent overshoot go 0.
Okay, so this is because this system that we wrote is not in the form that we want to see for percent overshoot. So when we wrote our time specifications, those were all assuming that we had a system where we were assuming we had a system squared plus 2 zeta omega n s plus omega n squared. Okay, our system is not like this. Our system is s plus 2 over I s squared, right? So because there's a 0 in the numerator, our time specifications are not exactly the equations that you've been given for them. So it's not going to be perfectly critically damped for the poles that we chose, but it is going to be very close. So what I wanted to also do was to simulate the system and show you the system behavior. So you can see that it behaves like a critically damped or an overdamped system. But the equation that I gave you for percent overshoot assumes that you have this form and this form only.
Okay.
Yeah.
Okay. Like, can you just know that, like, we already had the double,